So thanks for inviting me, and thanks for coming to the talk. I spent 3 wonderful years here, and it's the first time I come here since we left Princeton in 2020, in the middle of the pandemic. And yeah, it's exciting. Okay, so I won't assume any prior knowledge. So for some of you from Max and Natalie, it might be a bit boring, but still, I hope that I'll also get to some new stuff. So in the end, I have some open problems I wanted to share with all of you, and I hope we'll get there. But again, if there are questions about the basic definitions, I'm more than happy to discuss it and to challenge them and whatever. Okay, so yeah, so in general, this project is about this, mathematically modeling generalization, which is possibly one of the most important properties of learning algorithms, right? The ability to predict or to perform new tasks based on training tasks. And what we'll do today, so we'll first, I'll discuss the classical model for generalization, the PAC learning model. I will define it. Then we will see a modification of it, which seems very naive and simple, but it's extremely powerful in terms of expressivity. I hope I will convince you. And the last part will be about some open questions in this modified framework. Okay, so let's begin with PAC learning. So the goal here is to find a mathematical setting, a mathematical model, a computer TCS-like setting for studying algorithms that are able to perform such tasks, right? So they get a bunch of training examples, maybe of images, and each image either contains a dog or a cat, and then it gets a new image, and it should be able to predict whether this image contains a dog or a cat. Okay? So here we have just 2 options, dogs and cats. So how do we mathematically model it, or how was it modeled, by Valiant, Vapnik, Chervonenkis? So first of all, what is a learning problem? So it's just a distribution P over examples, right? So we have X represents the images in the example before, and we have just 2 alternatives, dog or cat, yes or no. And then what is the learning algorithm? So the learning algorithm gets a training set, we'll call it a data set, of examples that are drawn IID from B. And then it outputs a classification rule, which in principle for any given X predicts a label Y. And the goal is to correctly classify new fresh test points which are drawn independently of the training set. Okay, so the goal is to minimize the error, which is just the probability that this Hn, so n here hints on how many examples were used to train H. And the goal is to minimize this, what we call test error. Make sense? And the way one very important primitive in generalization is what we call the learning curve. We call it the learning curve, but it's actually a sequence. It's a sequence which the nth element of the sequence, right? So we have some distribution P, we have some learning rule that produces classifiers based on the distribution, and this pair defines a sequence. And the nth element of the sequence is the error, the expected error of the algorithm when trained on n examples. Okay, so to compute the nth element of the sequence, you apply your training rule on a random data set of size n and take another random point, and you test, you check the probability of error. Right, so maybe we imagine that for standard algorithms, this will monotonically decrease. This is actually not the case. Standard algorithms will have eventually it will monotonically decrease, but there will be bumps. You can it's highly non-trivial, but it's possible to transform any algorithm to a monotone one. But in any case, this is a very important primitive, right? This is what they do in practice. You take a bunch of data and of different sizes, and you test how well your algorithm generalizes on a particular problem. Okay. Now, in this mathematical framework of PAC learning, we assume that there is a known class of functions, and we further assume here in this talk that the target function, the target concept, the one we are trying to learn, the classification rule we are trying to learn is realizable with respect, so P is realizable with respect to the class. So there is a function, the target function is in the class, right? There is a function in the class which classifies everything correctly. Okay, so again, so H, the class of functions is known, but the target concept and the distribution are not known to the algorithm, to the designer of the algorithm. Make sense? So let's see an example. So let's assume H is a class of half spaces in RD, right? So signs of linear functions or affine functions, right? So how will the learning, how will the input of a learning algorithm look like? Right, so we'll get this training set. Some points will be labeled negatively, some will be labeled positively. And what is our goal? Our goal is that when we get a new point sampled from the same distribution, we need to classify the label of this point, right? So how would you classify this point? Minus, right? This is the only possible explanation if we know that the classification rule is a half space. But here, for instance, it's not clear, right? You could label it minus and explain it with a half space. You could label it plus, and this is the kind of task you have when you design learning algorithm to deal with uncertainty of this kind. So here it's not clear how to classify. Okay, great. So now let's define what PAC learnability means. Okay, so the basic observation is that if we just randomly guess the label, you know, you can learn any distribution with probability 1/2, right? We can just ignore the data and just flip a coin and guess accordingly. And a question which guides the definition of PAC learning: for which classes can we do better? Can we beat this thing, or maybe we can get arbitrarily close to 0. Okay, so this is the definition. So class H of functions is PAC learnable if there is a vanishing bound, so there is a sequence R of n that goes to 0, and an algorithm such that for every realizable P, the learning curve will be dominated by this sequence. Right, so for every P and for every n, the expected error of the algorithm after n examples will be at most this R of n, and R of n goes to 0. Okay? So pictorially, this is what it means, right? It says that so the red curves are the individual learning curves per distribution, and we have this R of n, this blue curve, which dominates all of them and goes to 0 uniformly. And you could ask here, why do we define it like this? I mean, why? Maybe it makes sense to flip the order of quantifiers and just require that each learning curve goes to 0, but not their upper envelope. And it's a valid question, and we also study such variants of the definition. But in this talk, we'll focus on the classical definition, which is this distribution tree workspace. Okay, so now once we have a definition, we can ask, you know, which classes are learnable and how. Right, so mathematically, can we characterize those classes of functions that are learnable? And maybe not less importantly, how do you actually learn a learnable class? Like, what are the algorithmic principles? So the first question is answered by this classical result which was discovered both in the East and the West. And it tells you that this notion of learnability is equivalent to, so there is an equivalent, mathematically much simpler definition, which uses this concept of VC dimension. So I will define it now. Right, so the theorem is that class H is PAC learnable if and only if it has a finite VC dimension. And let me tell you what is the VC dimension now. So the VC dimension is the maximum number D such that there exists, you can find D points in the domains, in the domain of the functions. And when you project, when you restrict your function class to these D points, you get to see all possible patterns. So any pattern on these D points, any binary pattern on these D points can be interpolated by some function in the class. Right, so it's the maximum D such that you can interpolate all possible patterns on the points. Okay. So this is the VC dimension. And not only do we know that PAC learnability is equivalent to a finite VC dimension, we also know that, this blue upper envelope curve, the way it converges to 0 is like D divided by the number of examples. Okay, up to, I think one half times this is a lower bound, and D plus 1 divided by M plus 1 in the numerator is an upper bound. So it's really, okay, so let's quickly discuss. So this is one of these theorems in mathematics where the finite VC dimension is a necessary condition. This is like a relatively easy fact. And the other direction is much more interesting. Let's go over the relatively easy fact together. So why is finite VC dimension necessary for learning? So let's assume we have a class with a very large VC dimension. We want to prove a lower bound on the number of examples, on the arrow after. So let P be a uniform distribution over a shattered set of a very large size, x1 up to xd. Okay. And imagine that the target concept that we're trying to learn, we pick it uniformly at random over all 2 to the d possibilities. So notice that no matter how I pick it, it will always be realizable. It will be a legal distribution, and there will be a constant class, 0 error. So that's great. Now notice that if the number of examples that the algorithm sees is at most d over 2, then the test point, right, the point which we are tested on, with probability at least 1/2 will not belong to them, right? And on this event, if you condition on the event that the test point is not among the points in the training set, we have no idea. Since H star was picked randomly, it could be 0 plus or minus 1 with same probability. So in this event, we're going to make a mistake. Any algorithm is going to make a mistake, probability 1/2. So altogether, we see that we have a lower bound of 1/4 on how many, on the arrow after d over 2 examples. And if the VC dimension is unbounded, so this applies for arbitrarily large d, and you have no convergence. Okay. As I said before, the upper bound is much more interesting, and it relies on a very nice and not complicated in retrospective symmetrization argument, which is due to Vapnik and Chervonenkis from the 60s of the 20th century. And it also underlies connections with other fields in mathematics and computer science. Okay, let's now go to the second question of how to learn. So it turns out that the proof of the upper bound, what I did not tell you, also gives you a very simple and intuitive learning principle, which is just, like pick any hypothesis in the class which is consistent with the sample point, right? So in the example we had before with the half spaces, you could pick anything, but, pick one thing and then always predict according to it. Pick any half space which is consistent with the, and This follows from the theorem that Vapnik and Chervonenkis actually proved, which tells you that if the VC dimension is finite, is bounded, is D, then with high probability for every, so notice with high probability for every function in the class, we will have that the empirical error, so the number of points it misclassifies on the training data, the fraction of points it misclassifies in the training data, is a very good proxy of the population error, which is what you want to minimize. Right, so in learning, you want to minimize the population loss. It is unknown. One thing you do know is the empirical loss. You can just count how many mistakes each hypothesis does. And for VC classes, these are approximately the same. Right, so it really reduces generalization, minimizing an unknown loss, to optimization, minimizing a known loss. Okay. That's the background. Any questions? No. Okay, so now we'll talk about more recent work. So, okay, so first of all, what is the motivation? So in practical, and not only practical, also theoretical problems, we often assume, or it's often the case, the data satisfies special properties that makes the learning much, much easier. So, for example, you can imagine that we have, we represent images, I don't know, using very large matrices or large vectors, but in fact, the real world images, they lie on a much simpler, lower dimensional surface. Or we often assume this is possibly the best studied problem in learning theory. We assume these half spaces like before, but now we assume it may be over a Hilbert space or a very large dimensional space. But we do assume that there is some margin, right? So you will never see points which are too close to the decision boundary. This is a very standard and well-studied assumption. And these kind of assumptions, if you try to now define in the classical setting, a concept class that captures it, it doesn't work. And we'll soon see that in some sense it formally doesn't work. And instead, what people did is, okay, we don't really care. The theory sort of inspired it, but now we can still talk about learning subject to these assumptions. And what we considered is to extend the classical theory by simply allowing partial functions. Okay, so we have no functions that are not defined over the entire domain. Each function comes with a support, if you will, some part of the domain where it's defined. And so, it's a very, very trivial move, right? But it makes things very interesting, it turns out. So that's some definition. So a total concept is just a total function from x to 0, 1. And a partial concept is a partial function. And the way we model it is that on part of the domain, it gives you a star. And star simply means that it's undefined there. So the support is all those points where it's defined. So this allows us to express data-dependent assumptions. So let's see some examples. So if we want to model a half space with margin, we simply define a function, a binary function, which, outside the margin, outside the area close to the boundary, it's defined according to the half space, positively or negatively. And here in the middle, it's just undefined, right? It's very easy. Similarly, we can do for these manifolds, whatever. And also, if you think about it, all the classical definitions extend very easily to partial concepts, right? So the slogan is that we just ignore the star because we're never going to see, right? Once we try to learn a concept, then there will be no, with probability one, we won't see anything like in the margin, we just ignore it, right? So what we are trying to learn is always distributions without stars. So star is ignored, and we have the same definitions as before, right? The same definition of PAC learnability, right? But we now, when we say realizable P, so we only think about distributions that are never supported on stars, and there will be some partial concepts and partial functions that explain them. We can also define the VC dimension by ignoring the star in the same way, right? we just ignore the stars, right? So again, we look at we say that the set x1 up to xd is shattered. If we project all function to this set and we remove all those guys that have a star, we still get to see all the binary cube. Okay? So again, we can ask the same question. Which partial concept classes, so how does it make a difference, right? So we just move from total concept to partial concept. Does the answer to this question changes? What do you think? You know, I know, but okay.
Probably it does change.
So to the first question, the answer doesn't change. So it still turns out that it will be PAC learnable exactly when the VC dimension is finite, and with the very same sort of convergence rate. However, the proof is dramatically different. I mean, the lower bound is the same. The upper bound proof is very different.
So you need a generally different algorithm?
Yeah, completely different algorithm. And in particular, this uniform convergence, what Vapnik and Chervonenkis studied, you know, that you have the uniform convergence of empirical probabilities to doesn't work. So, and this principle that we described earlier of just outputting something with low error on the data doesn't work. Like it doesn't play any role in the proof. And yeah, so the first answer is the same, but for very different reasons. And for the second answer, we don't have a good, for the second question, we don't have a good answer yet. So how to learn, we don't have like these positive general principles in the spirit of reducing generalization to optimization. We don't.
I mean, your algorithm doesn't give something.
It's, you know, it's like our algorithm that one include, like, you know, you do these orientations and it does involve some known algorithmic techniques, but it's much more complicated and it doesn't really give you something which you can explain to everyone. What we do know and what we did study and what I'll also want to present you some open questions related to is that it is in general impossible. So not only does uniform convergence and ERM are not sufficient, but in general, it is impossible to reduce learning of a partial concept class to learning of a total concept class, right? So you could ask whether, you know, for any partial concept class, we can come up with a total concept class and a reduction. So, right, well, what is a reduction in computer science, right? So you want you want to reduce task A to task B. So you want inputs to A to map somehow to inputs of B, and outputs of B to map somehow to outputs of A. And then whenever you compose it with a solution to B, you want to get a solution to A, right? That's a reduction. So I will not define it now for learning problem, but you just follow this route and you define it. So that's in general impossible. And I want to describe this a little bit now.
Can I ask you something? I mean, if you treat the star as just a third symbol, and you learn it as you're learning three different answers, then if you can do that, you can certainly do this. So
Right, but it's much harder, much more harder. So so half tests with margin, for instance, in high dimensional space will not be learnable with this interpretation of a star as a new label. And
I see.
okay, so again, so the question now I want to study is like, is it possible to have a reduction from a given partial concept class to any total concept class, such that if you learn the latter, you can also learn the former. And this turns out to, I will not tell you why, but it's not complicated, but it boils down to a very nice, my opinion, combinatorial question. Okay, so forget now about all these learning theory things. Still remember what the VC dimension is. So imagine now I give you this partial concept class. So some functions have stars in them or not defined. Now I want you to extend each function to the entire domain such that the combinatorial complexity will still remain bounded, right? So let's say the VC dimension of the partial concept class was 1, right? So there were never 2 points, x1, x2, such that you see all possible patterns. Can you somehow disambiguate these stars, zeros or ones? Sometimes they say 0, 1, sometimes plus, minus 1, I'm sorry. But I hope
It's on the, we can parse it.
Yeah, we can disambiguate it. Yeah. Right, so that's the question. So is it always possible to take partial concept class which is combinatorially simple and disambiguate it to a total concept class which is still combinatorially simple? And yeah, forget about that. Right, so this is the main question. I give you some concept class, partial class with finite VC. Can you disambiguate it such that the VC remain bounded? And by the way, VC is just one parameter. You can ask it for many other combinatorial parameters, and it's a valid question.
But didn't you just tell us that this shouldn't work?
Right, but can you find an example? Like,
okay, so.
Yeah, that's the question. So it shouldn't work, right? So we have a result that you can, there is concept class C with this dimension 1, so as simple as it gets. And every disambiguation of it must have like an unbounded, the proof here is really black magic. So it turns out that it's a simple relation, but it's a mysterious one to work in communication complexity and in graph theory. So in graph theory, it's the relationship between the pi-clique chromatic number and the chromatic number of the graph. So it was conjectured for a while that these two are polynomially related, and it turned out that they are not. The way it was proven that they are not polynomially related is by studying questions in communication complexity, relating, some sort of non-deterministic communication with deterministic, not exactly non-deterministic, but variants of it. And yeah, and it turns out there is so once you get this graph with small pi-clique partition number and a large chromatic number, you can very easily translate it to such an example. It works out really nicely. I can show it. I won't show it because I want to discuss the open questions. But if anyone is interested, I'm happy to discuss it offline. Yes.
Can you at least maybe say why it's supposed to be, like, why is it hard to find, like, why isn't there?
Yeah, you need to play around a little bit, right? So maybe the first guess is just like plugging zeros everywhere, right? But then, okay, so now I'm just taking you through the route I took when I started thinking about it. So, but try, so now let's assume you have a very large domain and you take all functions that are either stars or ones. So the VC dimension here is 0, right? You never see a 0,
yeah.
But if you plug in zeros everywhere, you get all possible subsets, right? It's insanely complicated. So here you want to just plug in 1 everywhere. So it doesn't, so these naive things don't really work. But maybe the open questions I will soon describe will elaborate on this a little bit in a way that will address your question. Okay.
Do we have some like necessary criterions on C, like for it to be complicated? Like, do we actually know that there is no hidden easier example? Like,
I don't. No. That's exactly my next. No. I really hope that there should be. Let's get there. Right. So how about natural? Like, as I said, this example is a result of a series of non-trivial reductions from some decision-tree problem through a communication problem through a graph thing, and then eventually you get it's a very long chain of reductions that you just lose. I just lose intuition when. So how about natural partial concept classes that we actually had in mind when we developed this theory? Like half-spaces with margin, right? So let's define finally now what half-spaces with margin are. So imagine we have, so the domain is the unit ball in Rn, and Rn can be even an infinite dimensional Hilbert space. Okay, so we just need inner product. And there is this margin parameter, which specifies the boundary, the distance from the boundary. And then for any unit vector, any vector on the sphere, we define a partial concept so that, you know, HU of X is positive if X is very correlated with U, so the inner product is more than gamma. HU of X is negative if the opposite happens, the inner product is at most minus gamma, and in between it's undefined. Question, can this be disambiguated? Can you somehow disambiguate the stars for every linear classifier?
Because in infinite dimensional Hilbert spaces, the half space question is already non-learnable.
Right,
Yeah.
right. So if you just, so one thing which we could do here is, okay, let's just disambiguate the stars here according to the inner product. But then the VC dimension will become N. Okay, so it's a no-go. I didn't say, the VC dimension here is just a function of gamma. It's 1 over gamma
Yeah,
squared.
I saw that, I asked like.
You saw it, I
perfect,
didn't. Yeah, so I didn't say it. Right, so the VC dimension here has no dependence on N, and you know, you can get, I don't care if you take gamma to be, you know, like extremely large, so it becomes 1. Even then, we don't know if you can disambiguate it in a way that I will soon tell you about some topological questions related to it, if it turns out to be related to topology, to Gauss of Ulam, variants of Gauss of Ulam theorem. Here is another even more embarrassingly simple question. Take any metric space, and let's assume that the diameter is 1. Take any metric space. And now, again, for any point in the metric space, we associate a partial function, which is positive if you know the distance. So HU of X is going to be positive if X is far away from U. So the distance is at least half diameter plus gamma. It's negative if it's close, if they're close to one another. So the distance is at most half minus gamma. And you know, if it's in between, if it's around 1/2, it's undefined.
The picture is reversed.
Yeah.
Yes.
I'm sorry, yeah. I did this like yesterday on the train. Again, yeah. Thanks. But it's clear, right? And you also see sort of why this is a generalization of the previous example. If we take the sphere and the inner products are like distances, right? L2 distances, good, excellent. And here it turns out, and this is something we just found out like 2 weeks ago, is that there is a magic number here of 1/4, and as long as gamma is more than 1/4, then the VC dimension is going to be 1. And this is just followed by triangle. Yeah, what else do you have? Triangle inequality, right? And somehow 1/4, and this is tight, right? You can find spaces which witness that 1/4 cannot be. But here's another question. So let's say that the gamma, the margin is more than 1/4. Is it true that for every metric space, you can find a disambiguation, right? So this is some sort of what you're asking, right? So this would be a simpler example for me, more intuitive, more geometric. Like if you can come up with a metric space such that you cannot disambiguate it by retaining the VC dimension finite, this would be, I think, a better example in some sense, maybe a step towards the half basis question. So even this we don't know. I have time, right?
You have time until 12:15. You start.
Good. No, I'll finish early. And so maybe I'll tell you some. We'll see. Okay. So yeah.
I guess with gamma being so large compared to the 1/2 and the diameter of 1, I mean, isn't this like for a sphere kind of almost like you're just dealing with antipodal points or balls around them?
Right. So for the sphere, maybe it gets. We need to do the calculation, but yeah. But this question is general. In sphere, it's true for any gamma, for an L2 sphere.
Yeah.
You can also, by the way, ask for Banach spaces, right? Which Banach spaces would it have of finite VC? That's and it turns out that this question in disguise has been studied by functional analysis. It's related to having very large dimensional L1 subspaces, like shattering L1 spaces. But this is very general. Any metric space, discrete, you know, whatever. Okay. So let me tell you now about an approach to study the first question about linear classification of margin, half-space margin. So it turns out that there is an independently interesting topological relaxation of the VC dimension, which plays an important role. So let me now, I will not fully define it, but I'll at least specify the simplicial complex that we use to define it. So, and it will be convenient to just take to assume that the concept class is finite. Now it's true that for half spaces, the partial concept class is infinite, but by compactness, if you're able to disambiguate every finite subclass, you can disambiguate the whole thing, right? So you can just pick a bunch of points on the sphere and only restrict to. So finiteness is not really a restriction, okay? That's my point. But it will make things more convenient. So we have now a finite concept class or a finite domain. Now look at the following set. So this set contains of all data sets. So these are sets of examples that are realizable by the class. Okay. So you look at all sets of pairs x, y, such that there exists some function in the class, which, you know, for every x, h of x is the y. Make sense? What can you tell me about this this set? It's a simplicial complex, right? If a data set is realizable and you just remove point, the same function that realize it will still realize the. Okay. Moreover, in the simplicial complex, the vertices are just the examples, x, y, right? So for every example, we have an antipodal example, x plus x minus. So it's a simplicial complex where you have also an antipodality relation in the vertices. And the facets, the maximal faces, what are maximal data sets that are realizable? Let's take the whole function, right? All the pairs that define the function. So the facets are the concepts. Make sense? So here's an example. We have here 3 vertices, which means we have 6. We have 3 points in the domain, so we have 6 vertices in the complex. And you know, and the simplicial complex is exactly those. So the maximal facets are exactly those colorful triangles, right? And this one is alone. Nobody labels 3 with plus, so it's not. Okay. Okay. So what is the VC dimension in this complex? So now I give you a bunch of data sets of size D that are shattered. What does it look like geometrically? What does it correspond to?
The dimension of the complex, maybe? Yeah.
No, the dimension of the complex, if we avoid modalities, is just going to be the size of n, right? The size of the domain. We just take these maximal facets, right? So we don't really want to work with the naive limits. We really want to take antipodality into play here. But let's go back to this question. So I give you a shattered set.
Like a cube.
Almost dual of a cube. It's the L1 sphere, right? So you get an L1 sphere. So yeah, so shattered set, right? So for example, here we have a shattered set. So we have 1 minus 1 plus, 2 plus 2 minus. So ignore these 3 in the middle, right? So we have, if this is one basis vector, this is the negation of it. This is another, this is the negation of it. And then every yeah, like if you look at it as a continuous complex, you just get everything in between as a realizable distribution. Okay, so it's so the VC dimension is basically, so this is called a cross polytope. cross polytope is the boundary of the L1 sphere, and combinatorially it's just right. So we have a set of size 2n, and simplicities are all subsets that contain at least one, exactly one, or at most one from every pair. So the facets are exactly one from every pair, and so you can believe me that combinatorially this dimension is just the largest cross polytope in this complex. And the spherical dimension, you just take the dimension of the largest antipodal sphere in delta of C. So this is how we define the spherical dimension. So the spherical dimension of a concept class, you look at this implical complex and you ask yourself, can I find as a subcomplex something which is homeomorphic to a sphere and has the same antipodalities, right? So if a simplet is there, also the antipodal simplet should be there. Right, so as I said, we have this antipodality structure on our space because every example had the negation. Okay?
So basically replacing cross polytope by some others.
Right. So clearly, the VC dimension is a lower bound on spherical dimension, right? If the VC dimension is D, I can find a cross polytope of dimension D. But maybe I can find like an L2 triangulation of the L2 sphere of dimension 2 to the D, you know, like maybe I can find things that are much larger. So the VC dimension is lower bound. And an open question is, what about the converse direction? Is there any function such that the spherical dimension is upper bounded by this function applied on the VC dimension? And this is equivalent, this question is equivalent to the existence of non-trivial disambiguations of the half-space margin, right? So more concretely, so the following two are equivalent. The spherical dimension is at most some function of the VC dimension, and you know the dimension of the Ennian disambiguation must go to infinity with the Euclidean dimension. Here is a related open question, which is a bit more accessible, I think. So it's related in, I think it's equivalent almost, but it's not formally equivalent. But I believe that, you know, if we resolve this one, then we can also resolve the other one, or at least I hope. But it's at least more accessible. Okay, so let me ask it. So let's say you have, can you cover Rn by open sets? Okay, open cover of Rn by open sets with bounded diameter, let's say 1. Can you do it with sets that are combinatorially simple? So the VC dimension of the cover is order of 1. Right? So I want to, right, so you could take, for example, balls, cover it with balls, but the VC dimension will depend on, right, or balls is whatever, d squared, I don't know, n squared, some polynomial n. You could cover it with boxes, you could cover it with, you know, any, you know, polytopes, whatever. But all these natural geometry covers also have large combinatorial complexity. The VC dimension is large. Can you cover Rn with sets of bounded diameter that are simple combinatorially? Now, why do I ask bounded diameter? Anyone sees? If the diameter is not bounded, I can just take balls, concentric balls, like a chain of balls, right? So a unit ball, a ball of radius 2, a ball of radius 3, a ball of radius 4, and so on. And combinatorially, what I have is a chain of sets, which has VC dimension 1. So chain of sets, chains have VC dimension 1. So that's why the bounded is important. Yes.
What do you think the answer is?
So finally, I have more intuition. I think the answer here is that you cannot disambiguate. Like now I need to remember how exactly the relation is. So I think you can. Yeah, you cannot.
Yes,
You cannot. Yeah.
But the first question is kind of not related to Rn, right?
It's related to Sn.
Because spherical is
Yeah.
in there, yeah, but more,
Right. So this is how I like. So if you want a question which is even more related to this one, but still not quite equivalent, is can you take Sn? Now, instead of bounded open cover, you want an antipodal cover. What is an antipodal cover of Sn? So this is like in both Coulomb, those of you are familiar. So these are sets that, so a set is antipodal if it does not contain x and minus x. So can you antipodally cover Sn? Right, so Bose-Coulomb theorem tells you, or one of its variants, that any antipodal cover of Sn must have at least n+1 sets. So in some sense, it says that there are no antipodal cover of Sn, which are combinatorially very simple, containing just few elements. And what we're asking is, can you antipodally cover Sn such that this dimension remains bounded? And here I just replaced antipodality by boundedness to make it even more accessible. So the antipodal, so I think for the antipodal cover, it will be a corollary of our conjecture. This is not formally a corollary, but at least it's morally related. Let me tell you that spherical dimension has relevance in other questions in learning theory. So it gives us the best lower bound on replicable learning, which is something that Max studied. So in replicable learning, you want learning rules that are replicable. What replicable means that, if you apply it twice on two independent data sets, then you get approximately the same answer. All right, so you want replicability of experiments. So if you think about training on a data set as an experiment, you want this experiment to be replicable. So it gives us the best lower bound on things related to replicability. So number of random bits. This is Max's work. It also gives us the best lower bound on reductions from classification problems to optimization problems, right? So the way we actually learn problems in this world is by solving optimization problems, right? So we introduce these surrogate losses, we have parameters of the deep neural network, and then we never actually minimize the work directly with the classification 0-1 loss. We use surrogates, we take gradients, we do backprop, right? So and every such algorithm can be interpreted in the language of TCS as a reduction, right? You have a learning problem on a classification problem, and you reduce it to a stochastic optimization problem. And then you can ask, is it true that any learnable classification problem can be reduced, as we see in the real world? Is this phenomenon also, as it's also true in general? So the spherical dimension gives us the best lower bound, best known lower bound on how large a dimension in such reductions can be. And last application is even more general. So you can, instead of taking these geometric objects, you can take a combinatorial abstraction of them, and it still works there. And by the way, it could be that it's also an upper bound in each of these cases. So it could be that it characterizes it. So far, we just know it's a lower bound. And here I should advertise these three, Tom Vapnik, Zachary Chase, and Bogdan Chornomaz, or work with me. Okay, Zach doesn't work with me anymore, but he used to. He worked with me, I just don't pay him anymore. Yeah. And I think that's it. So, right, so let's just recap. So what did we discuss? So at first we discussed this PAC learning framework. Then we considered this very simple extension by allowing partial functions, and we saw that it really buys you flexibility. It becomes very easy to represent these data assumptions on data. That it's not clear how to represent otherwise. And then we sort of formally argue that it is indeed more expressive. You cannot reduce any partial problem to a total problem. This theory is really more expressive than the. But then we asked, what about natural classes that are very easy to present in the partial world? Can they also be presented in total world? And this gives us some nice purely mathematical questions in combinatorics and topology and geometry. And yes, thank you. We're even time for lunch, right?
Maybe before we move to questions, I'd like to mention that Shay speak at the theory lunch on Friday.
Hmm.
Yeah, I don't know if you're.
On privacy, on differential privacy.
Send something else.
Linear algebra.
Privacy.
Yeah.
Any comments or questions?
Yes,
I guess this isn't what you talked about so much, but you mentioned that there's a way to make the learning curve always monotonic.
Mhm.
Recently.
yeah, it's a nightmare. Yeah, okay.
Just that.
It's hard. So it's we wrote a paper on this. It was in fall 21, I think, or 22. Monotone learning. It's you can visit my homepage, and it's very complicated. Like you need to add noise in a very tailored way. That you really need to battle these very esoteric extreme cases, and we do it by handling noise in a controlled way that allows you to. But if you just take a off-the-shelf natural language algorithm, it will be non-monotone. So this question was whether there exist monotone learning curves was asked by Lugosi and Devoy, and they show that if you just take classical learning algorithms, that they are non-monotone, and they even argued conceptually that you must be non-monotone if you want to learn very consistently, because and they had some philosophical explanation for that sometimes you encounter new phenomenon and then you need to sort of rethink, and when you rethink your error goes up a little bit, but anyways, it's not true. You can make everything monotone, and yeah, but it's complicated. It's very technical, the
Interesting.
transformation. Yeah. Yes.
So in the proof of your impossibility of like partial to total learning,
Mhm.
like, is the algorithm allowed to like look at the data given, like for partial learning, and then
No.
so based on
no.
this, change its labels? Oh, it's not allowed.
No. So a reduction, right? So you have like you take input to the partial probe. So you take
Yeah.
labeled example here. You
Yeah.
translate them to example here.
Yeah,
And then you solve the total
Yeah.
problem, and then you have another reduction in
Yeah.
on the output space that takes a solution hypothesis here
Yeah.
and maps it back here. So formally, the way we defined it is not. It's like what was called either Turing or the other reduction.
11 reduction maybe,
Yeah,
because it maps solution.
right. Inputs to inputs, solution to solutions. It's interesting to study the more rich
Oh, I
reductions.
mean, I was asking like what you just described is like the first part of what you described is what I was asking. Like so it could be any algorithm that looks at like all like the partial data and makes it.
So the reduction you can do however you want,
Okay,
but later it should compose with any solution
yeah,
to the problem you reduced.
yeah, but there's like no restrictions on the
No.
algorithm that like maps.
Right. Yeah, so the disambiguation is, on the face of it, it's a very naive reduction, but it
Yeah.
is in fact, it captures also more complicated
Okay.
reductions.
Okay.
Okay, cool.
More questions? Okay, we can head to lunch. Thank you.